Hello AP Chemistry and welcome to 17.3 acid-base titration. So now we need to understand salts. We need to understand the identification of weak acids and versus strong acids. And then we also need to know how to do all the calculations that we've talked about to date, right? For example, weak acid pH titration calculations versus strong acid pH calculations, and then how to know when to do either of those. All right, so first, the concept of a titration is unchanged from what we talked about in chapter 4, right? So here we always have our known solution in the burette, right? We have an unknown solution in the vessel below, right? And the whole point of known concentration is if that I know my molarity and I know the volume delivered, right? That means I also know moles, yes? And then I can relate those moles to, right, the moles of unknown via a mole ratio, right? I don't know why I wrote that way. Via a mole ratio, right? Now, all that unchanged, right? The setup of a titration, right, is the same too, right? We got our burette, we got that. We've got our fancy little stir bar down here, right, if we have such a tool, right? Otherwise, we could just do with some swirling, or we could stop and stir intermittently, right? Likewise, depending on the type of pH probe we have, we could also use that to do our stirring, right? And then obviously that will give us an instantaneous read on our pH as we do our experiment, right? Which can lead to useful information like the equivalence point and a titration curve, which obviously can be useful in a lot of different ways. All right, so basic setup. All right, so let's talk a little bit about a strong acid titration. First of all, let's talk about our equation, right? So if we had a strong acid like we do over here, right? So we have 50 mils of 0.1 molar HCl titrating with 0.1 molar NaOH, right? So if we think about our setup, right, this is in the burette, right? This is in the flask below, or beaker or whatever, right? But in the vessel below, we have our HCl, right? 50 mils of it. And knowing the molarity and volume of NaOH added, we will be able to calculate the moles that are present in that HCl, right? Okay, so it's also important that we have a reaction because that's always important to look at, right? So if we have HCl plus NaOH, right, clearly that's going to make H2O and NaCl, right? We understand this will be aqueous, this will be a liquid, right? And we're good to go. So let's go ahead and identify the important parts here. So first of all, at this beginning point, right, what's super important to note is that reflects just the thing we are analyzing, yes? That reflects only, right, our HCl solution. And if we think about what that means in terms of which species are present, it, because it's a strong acid, dissociates completely. Meaning we have a whole bunch of H plus and a whole bunch of Cl minus, and that's it, right? Which is why for a strong acid, we typically have a very low pH. For a strong acid titration, we typically have a very low initial pH because my acid is completely dissociated and there's a boatload of hydronium ion floating around in the solution, right? And then you'll see that we slowly start to add some base. Okay, now, the whole time we are adding base, the base is, right, the base is limiting, yes? The base is limiting as we are adding it, right? Meaning that at no point in time, thus far, right, is there any buildup of sodium hydroxide in the solution because all of the hydroxide is going towards this neutralization reaction, right? We are getting a buildup of sodium ions and chloride ions, right? Because those are spectator ions that are just hanging around, right? So we might even be better off saying the net, right, which would be H plus OH minus, gives us water, right? And so then if we think about that, right, we have this buildup of our sodium ions and our chloride ions, neither of which affect the pH of my solution, right? Things to think about. And then as we keep adding it, right, eventually we get to 50 mils, and we should have been able to predict, right, that 50 mils is when we would reach the equimolar condition, right, where we have added equal moles of NaOH that are equal to the initial moles of HCl present, yes? The moles of NaOH added are equal to the moles of HCl originally present, right? And we want to make sure we don't shortcut that wording there so we don't confuse ourselves, right? Because at this point in time, right, like it says here, right, that H plus is completely neutralized by the hydroxide ion, right? Meaning there is neither H plus nor hydroxide ion in significant quantities at the equivalence point in a well-done titration, right? All we have are our products, which are water, right, and our aqueous sodium chloride, which, since sodium chloride is composed of conjugates of strong acids and strong bases, has no effect on our pH, which is why our equivalence point pH is 7, yes, because it reflects the pH of aqueous NaCl. Yes? All right, then should we continue adding strong base? Obviously now, for this whole region, we have an excess base scenario, right? Which means that anytime we go past the equivalence point, so any addition past 50 mils, starting with the 50.10 or 50.01, depending, you know, from that moment on, the quantity of base added is what determines the pH of my solution, yes? All right, because there's nothing left to affect our pH at that point in time, right? Another thing to think about, right? So up until this equivalence point, right, our predominant pH is our aqueous HCl, right? And you'll see that from our initial point up to where our steep rise happens, right, you'll see that this change in pH is only about 1 pH unit, right? That change in pH is only about 1 pH unit because our acid is completely dissociated, which means that the overall concentration of hydronium ion doesn't change a whole lot, right, until we near the equivalence point. Yes, does that make sense? Okay. And then we get this very steep portion here, and that part is very long for a strong acid titration, right? And then the other thing to note here, right, so let's clear up a little space here first. The key thing to note here, and the reason why, going back to what we did previously, the reason why titrations are hard is you'll see that this steep rise falls in a very narrow window, yes? From maybe like, we're talking, if this is 40, this is 45, right? So we are talking less than a milliliter. It makes the difference between the beginning of this steep rise to the end of this steep rise is less than 1 milliliter, right? Which is why finding that endpoint is so challenging, right? And requires you to be quite meticulous in order to do a very good job. Yes, does that make sense? All right, so this is a strong acid titration. If on the flip side we were looking at a strong base titration, we would do much the same, right? So here if we have 50 mils of 0.1 molar strong base with 0.1 molar strong acid, right? We know that this is the thing that is in our burette this time. Nope, sorry. This strong base is the thing in my beaker. I'm titrating it with this in my burette, right? And then if we were to write out my equation, right? So I didn't give this an identity, but if we just have strong base plus strong acid, doesn't really matter, right? It is going to give us H2O plus a salt, right? Okay, good enough, right? So then if we think about what happens here, right, it's just like before, just opposite, right? So at this initial point, this reflects just strong base, yes? As in that's all that's in the solution. Because it's completely dissociated, really it's just the total hydroxide ion present, yes? Because all that strong base dissociated into its respective amount of hydroxide ion, yes? So good here. And then same principle right down here, we have an equivalence point. We're at that equivalence point, the amount of acid added equals the amount of base, moles, initially present, therefore neither are present at this point. Yes, they have completely reacted, and all we have is H2O and our salt. That salt is the conjugates of a strong acid and strong base, which has no effect on pH, because it has no tendency to be acidic or basic, which reflects a pH of 7, right, for that particular salt, yes? And then, right, if we continue onward for this whole section, we have excess acid, and so every drop of acid now dissociates completely in that solution, and that's what determines the pH from every drop after we reach the equivalence point, yes? And in terms of strong titrations, right, we should note, right, that this region kind of looks the same, right, in that pH changes only about 1 pH unit before we get to that steep part, right? Again, that steep part happens over a very narrow window in terms of milliliters, right? And pH of 7 at the equivalence point. Good? Thank you for listening. Be good, and I will see you soon. We will do some practice problems in the next lecture. Have a good day. Bye.